The eelgrass was gone. Algae had won. Every remediation effort had failed. The nutrient pollution was simply too heavy. Then 4 sea otters moved in. AIM Dr. Raymond Finch, and what happened next dismantled everything we thought we knew about dying estuaries. This estuary didn't just survive the choking. It exploded back to life. And the mechanism was something no engineer had budgeted for. Elkhorn Slough sits at the edge of Monterey Bay, where farm runoff drains off some of the most productive agricultural land in California. The water smells of it, a green-gray heaviness that coats the back of your throat. Strawberry fields and artichoke farms run right to the slough's edge. Their nitrogen drains into it with every rain, every irrigation cycle. By the early 2000s, the nutrient load had rewritten what lived here. Surveys confirmed the slough had lost more than 60% of its eelgrass beds. Nearly 40 hectares of living habitat had been reduced to bare gray sediment, flat, silent, and biologically empty. Eelgrass doesn't disappear quietly. When it goes, everything that sheltered inside it goes too. Juvenile fish, invertebrates, foraging shore birds. The mudflat becomes a desert with tides. The textbook prediction was simple and merciless. Excess nitrogen fuels algae blooms. Algae blooms block sunlight. Without light, seagrass dies. Every model pointed the same direction, down. The farms had not changed. The nitrogen had not dropped. Nothing in the water column had shifted to suggest a recovery was coming. Then Brent Hughes pulled his monitoring transects. Hughes, a marine ecologist at UC Santa Cruz, had been tracking eelgrass extent since the early 2000s. What his transects returned in 2012 made him reread his own data. Dense, healthy eelgrass, growing in the same nitrogen-heavy water that was supposed to have killed it. The nitrogen readings were still punishing. That number should not produce a seagrass recovery. It produces a green catastrophe. The eelgrass did not know that. Hughes traced the recovery backward through every variable: water temperature, sediment chemistry, tidal patterns. None of them had moved enough to explain it. Then he looked at what was floating on the surface. A sea otter on its back, cracking a crab between its forepaws, does not look like a water quality engineer. But that is exactly what it had become. I spent 40 years watching ecosystems collapse. The most important variable in a dying system is almost never the one you are measuring. Stand on the observation deck above Elkhorn Slough on any clear morning, and you will see exactly what the postcards show. Herons stalking the shallows, harbor seals sprawled on mud banks, a channel that looks full of life. That postcard is a lie the surface tells very well. What it hides is a decades-long collapse happening 30 centimeters beneath your line of sight, in sediment that was once a living floor and had become bare gray mud. The geography of that collapse is worth sitting with. At the mouth near Moss Landing, seagrass density had fallen below 20% of its documented 1930s extent. The seals hauled out there were resting on a mud flat, not an ecosystem. In the upper channel reaches toward Elkhorn Road, dissolved inorganic nitrogen ran at concentrations 2 to 4 times above what seagrass physiology can tolerate, chemically hostile to the very plant that once held the sediment together. Along the southern tidal flats beside the Union Pacific Rail Corridor, seagrass had vanished entirely from stretches that once sheltered Dungeness crab and Pacific staghorn sculpin nurseries. A silence that took less than 2 decades to become complete. In the mid-channel plots Hughes and his team established as permanent monitoring stations, epiphyte loads on surviving seagrass blades had grown thick enough to cut photosynthesis by more than 60%. The plants were being shaded to death by organisms living on their own surfaces. That last number is the one that stops you. 60% of photosynthetic capacity gone, not from the pollution itself, but from the biological film the pollution fed. The seagrass was not drowning in the nutrient load. It was being buried alive by what that load grew on top of it. Brent Hughes went into his study at UC Santa Cruz, expecting to document a clean, linear story. More nutrients in, less seagrass standing, confirmation of a textbook prediction. The survey data did not cooperate. The collapse was not uniform across the slough. Patches of seagrass were holding on, dense, structured, rooted. And those patches did not appear randomly. They clustered in specific reaches of the channel, precisely the sections where sea otter sightings had been logged most frequently in the years just before the 2012 transect surveys. The zones without recent otter presence continued to degrade. The zones with it did not follow the script. Hughes published those findings in 2013. Dissolved nitrogen at the recovery sites was still running at 4 to 6 milligrams per liter, well above the threshold that should have made seagrass survival impossible. The pollution had not eased. The farms had not changed. The seagrass had no reason to be there. It was there anyway. Something had broken the chain between pollution and collapse, and, whatever it was, it operated only where the otters had settled first. Hughes had the result. He did not yet have the mechanism that made it possible. I have seen this pattern in other systems, a number that should not exist, sitting quietly in a field report, waiting. The data does not explain itself. You have to follow it into the water. Restoration crews arrived at Elkhorn Slough with gloves, waders, and a plan. They pressed individual eelgrass shoots into bare sediment, row by careful row, across degraded mud flat that had been silent for years. The work was meticulous. It was also, as the data would eventually show, aimed at exactly the wrong target. The missing variable was never a plant. It had teeth, fur, and a metabolic rate that demanded 25% of its own body weight in food every single day. Land managers had committed more than a decade of negotiation and millions of dollars to nitrogen reduction. Buffer zones installed along farm drainage channels, sediment traps, funded through public conservation grants. The investment was real. The outcome was not. Manually planted shoots held through their first growing season in a handful of test plots. Then the epiphyte load returned, algae blanketing each blade, and the replanted beds went dark within 2 years. Nitrogen in the water column never fell below the threshold eelgrass physiology required. The system kept sliding regardless. Nobody scheduled what came next. The southern sea otter population along the California coast had been recovering for decades, and by the mid-2000s, the animals pressing southward had simply run out of territory. They followed the food. Elkhorn Slough was in the way. They moved in, no budget, no environmental impact report, no restoration plan on file. They arrived because they were hungry, and the estuary had crabs. That is the entire explanation. Brent Hughes and his monitoring team at UC Santa Cruz were running transects when the eelgrass beds in otter-occupied areas began doing something the hand-planted plots never managed, stabilizing, then expanding. In water, still carrying that, should have made recovery impossible. The California Department of Fish and Wildlife had formally flagged portions of the slough as low priority for wildlife recovery. Water quality deemed too degraded to support eelgrass-dependent habitat. Hughes's 2012 transect data told a different story entirely. The otters had not read the assessment. What the otters were doing to the crab population, and what that pressure released further down the food web, was not part of any restoration model the agencies had built. The mechanism Hughes suspected was operating below the surface, inside a trophic cascade 3 links deep, in a system nobody had modeled for this estuary. Every dollar spent replanting eelgrass by hand had addressed the symptom. The predator that was missing had been suppressed along this coastline for the better part of a century. and its absence had quietly restructured every layer of life beneath the waterline. Putting the chutes back in the mud was never going to fix that. Hughes now had a recovery expanding in water that should have stopped it cold. What he needed next was the invertebrate count, the grazer data, from inside the beds where the otters had been working longest. That number would either confirm the cascade or dismantle everything he thought he understood about how this system had come back. The invertebrate count came back, and what Hughes found inside those otter-occupied channels was not a gradual shift. It was a cascade, running faster than his own models had predicted. The sequence started with a single, unglamorous act, an otter diving, locating a crab and eating it. The graceful crab and the lined shore crab had been building for decades in the absence of any real predator pressure. Their densities inside the slough had reached a point where they were functionally suppressing an entire community of smaller invertebrates, animals that had nowhere to go and no defense. A single otter at Elkhorn weighed roughly 27 kilograms. It was pulling that fraction of its own mass in crab out of the channel every single day. Not occasionally, not seasonally. Every day without pause, driven purely by a metabolism that cannot afford to stop. Within a single season of sustained otter foraging, the crab pressure dropped. Sea slugs, isopods, and amphipods, the tiny grazers the crabs had been cropping back, began to rebound, their populations built quietly in the sediment and on the blades before Hughes's team had finished counting. Follow the chain as Hughes mapped it. Otters suppress crabs, crabs release the grazers, grazers strip the algal epiphytes from the plant surface, light penetrates the blade, photosynthesis resumes. 4 links, no engineering, no invoice. Each one triggered by the one before it. Those grazers were doing something no restoration crew had managed, cleaning the leaves from the inside of the habitat, one blade at a time, around the clock, at no cost to anyone. Hunger was the only engine. It did not clock out. Hughes measured the results in otter-occupied zones against otter-free zones in the same slough. The dissolved nitrogen in both zones held steady at 4 to 6 milligrams per liter. The pollution had not moved. The plant coverage had. That number should not have been compatible with a recovering seagrass meadow. And yet, the pollution had not changed. The physics had changed. That distinction is the entire argument, and it took Hughes years of transect work to make it stick in print. Then something else began appearing in the monitoring logs. Juvenile fish, invertebrate recruits, species using the recovering canopy as nursery ground, the full architecture of a coastal estuary, piece by piece, settling back into place around a plant that had simply been given back its light. The otter did not clean the slough. It freed the creatures that cleaned the leaves. The leaves did the rest. But Hughes's logs from the outer reaches of the slough, the zones where otters had not yet established, were showing something his chain reaction model had not accounted for. Hughes's logs from the outer reaches of the estuary showed a system no one had designed. The recovery was real. It was also, in certain corners, genuinely inconvenient. Females with newborn pups were documented nursing within 30 meters of active aquaculture cages at the Moss Landing Harbor entrance. Wildlife managers had not modeled this use for a waterway carrying that level of agricultural runoff. The problem was specific, and it was learned. Individual animals identified the aquaculture gear, returned to the same coordinates repeatedly, and the behavior spread through the local group. Oyster and clam growers reported losses they could measure in dollars and in missing trays. A wild predator does not read cage labels. It reads depth, current, and the smell of prey. That is not a behavioral flaw. It is a behavioral fact, and it arrived faster than any management plan had prepared for. At the same time, the recovering eelgrass was doing something its own modelers had not fully anticipated. Dense, expanding bedstrap fine sediment. Tidal flow geometry and portions of the estuary shifted measurably as the beds grew back toward their former extent. Kayak tour operators who had navigated the same corridors for years found shoaling in channels that had been reliably open. The physics of recovery had quietly redrawn the waterway beneath them. Hughes was candid about it. In interviews following his 2013 publication, he stated plainly that the cascade he documented was genuine. But the estuary rebuilding itself was not the bounded managed system conservation plans had described. It was wider than that. It was older than that. This is the part that made me stop and reread the field notes. The data confirmed recovery. It also confirmed that the recovered system had immediately begun exceeding the boundaries anyone had assigned to it. A living system expands according to its own logic. It does not negotiate with the infrastructure that grew up around an estuary everyone assumed would stay degraded. That friction between the recovering wild and the settled human is not a failure of the restoration. It is its proof. The question now hanging over Elkhorn Slough is not whether the recovery is real. It is whether the people who depend on this estuary can build new rules fast enough to keep pace with a wild system that is not waiting for permission. Not a miracle. That is the first thing Brent Hughes said when people started calling it one. He had spent years pulling transects through nitrogen-choked water, and what he saw was not magic. It was a mechanism clicking back into place. A predator disappears. A crab population swells unchecked. The invertebrates that graze algae off eelgrass blades get eaten down to nothing. The blades go dark under a thick algal coat. The beds die. Every step is physics. Then reverse the chain. The otters return. The crabs thin. The grazers come back. The blades get scoured clean. Light reaches the roots again. The beds grow. You could set a clock by it. Here is the number Hughes published in his 2013 survey that I have not been able to stop thinking about. Dissolved nitrogen in the slough was still reading at the time of the observed eelgrass rebound. That concentration should not support a bed recovery. The textbooks say so plainly. The textbooks were solving the wrong problem. They assumed water chemistry had to change before the beds could return. What Hughes et al. Showed is that a biological mechanism, a 27-kilogram mammal eating crabs, was doing the cleaning the nitrogen never did. The cascade has 4 trophic levels you can trace without a laboratory. Otter pressure suppresses crabs. Crab suppression releases grazing invertebrates. Grazer abundance strips algae from blades. Clean blades photosynthesize at full capacity and the bed holds. What the Elkhorn data cannot yet explain is why the grazer rebound outpaced every projected timeline Hughes had modeled. The invertebrate communities rebuilt at nearly 3 times the rate the colonization literature predicted for a nitrogen-loaded site. The mechanism behind that speed has not been pinned down. What I keep returning to is the simplicity of the lesson. The slough did not need cleaner water. It needed one predator back. Once that predator arrived, the slough remembered everything else without being asked. That is not hope. That is stored ecological memory running its program. Share this with someone who still believes the damage is permanent because the evidence says otherwise. Drop your region and one species you have personally watched disappear from your area in your lifetime. And yes or no in the comments. Have you ever seen something come back that you were certain was gone for good? Because if the answer is yes, I want to hear that story. The wolves of Yellowstone's northern range graze 90% of the riverbank willow, covered down to bare soil across 70 years of elk pressure. The U.S. Fish and Wildlife Service spent 3 decades resisting reintroduction before the 1995 release. And within a decade, the rivers were physically changing course. What nobody predicted was what happened to the songbirds, and that thread is still not fully closed. I'm Dr. Raymond Finch. I'll see you in the field.